So we discussed about gaseous state in this chapter. We mainly discussed about deviations from gas laws and causes of deviation from ideal behavior. Next one is volume correction, pressure correction, and Wonderwalls equation. So mainly what is important topic is the isotherms of carbon dioxide, critical phenomenon, critical constant, determination of critical constant. These are the main topics in this chapter. We are going to discuss about these clearly. First of all, we have to see the what is the gaseous state, what are the Boyle's laws and Charles' law and Avogadro's law. In this chapter, as a gas which obeys Boyle's law, Charles' law, etc., under all conditions of temperature and pressure is known as ideal gas or a perfect gas. Further, since the gas equation PV is equal to nRT is derived by combining Boyle's law and ideal gas may be defined as a gas which obeys the gas equation PV is equal to nRT under all conditions of temperature and pressure, and hence the gas equation is also known as ideal gas equation. However, no gas is perfect, and the concept of perfect gas is only theoretical or hypothetical. Gases tend to show ideal behavior more and more as the temperature rises above the boiling points of their liquefied from and the pressure is lowered. Such gases are known as real gases. Thus, a real gas may be defined as a gas which obeys the gas laws under low pressure or high temperature. All gases are real gases. They show more and more deviation from the gas laws. As the pressure is increased, the temperature is decreased. As mentioned above, gases tend to show ideal behavior as the temperature increases above their boiling points. Thus, at ordinary temperature, the most rarely ideal gases are those which have very low boiling points, that is, nitrogen, hydrogen, oxygen, etc. On the other hand, the most easily liquefiable and highly soluble gases, carbon dioxide, sulfur dioxide, ammonia, shows much larger deviation from ideal behavior. Deviation from gas law, deviation from Boyle's law. According to Boyle's law, PV is equal to constant at constant temperature. This means that at a given temperature, the product of PV should be constant at all pressures, and thus the plot of PV versus P at constant temperature should be a horizontal line. However, this is an ideal behavior which no real gas shows in practice. All gases give either of the following two types of curves. You see in slide clearly. In this plot, in this graph, the graph in between PV and pressure, the horizontal line, dotted line shows the Z is equal to 1. That is the real gas. However, carbon monoxide and methane shows the negative deviation. That means they does not obey the ideal gas equation, does not obey the ideal gas properties. So below the dotted line, slide clearly observe these two are the negative deviation, and hydrogen and helium are the above the horizontal line. These are straight lines. So that Z is greater than 1. Z is greater than 1. For gases like hydrogen and helium, the product PV continuously increases with increase of pressure. For gases like CO and CH4, the product PV first decreases with increase of pressure, reaches a minimum value and then begins to increase. These curves lead to following conclusions. First one is at low pressure, PV for all gases except hydrogen and helium has a lower value than that of for an ideal gas. Second one, at high pressure, PV for all gases including hydrogen and helium has higher volume than that for an ideal gas. Third one, as per as pressure approaches zero, all gases tend to behave as ideal gases. Alternatively, the magnitude and the nature of deviation from Boyle's law may be observed from the plots of PV nRT, that is compressibility factor, which is denoted by Z. Compressibility factor Z is equal to PV by nRT. At constant temperature and compressibility factor is directly proportional to PV. Remember that at all temperatures and pressures Z is equal to 1, that is ideal gas. The plots of compressibility factor Z versus P at different temperatures for nitrogen gas are shown in figure, shown in slide clearly. You have to observe the slide and you have to observe the graph. The graph in between compressibility factor, that is Z, and pressure. You see the ideal gas, that is the dotted line. Ideal gas, that is equal to 1, that is compressibility factor is equal to 1. You take the at lower temperature, that is for example you take minus 50 degrees centigrade and 0 degrees centigrade and 50 degrees centigrade. These are the lower the horizontal line. Above the horizontal line, that means 100 degrees centigrade, 50 degrees centigrade, 0 degrees centigrade and minus 50 degrees centigrade. These are negative curves. These are in negative or lower temperatures are negative. As the temperature increases, the dip in the curves becomes smaller and smaller. At a particular temperature, at 50 degrees centigrade in case of nitrogen, the curve seems to remain almost horizontal and Z is much closer to 1 for an appreciable range of pressure 0 to 100 atmosphere in the present cases. Thus, temperature at which a real gas behaves like an ideal gas or an appreciable pressure range is called Boyle's temperature or Boyle's point. Below this temperature, the value of Z at first decreases, approaches a minimum and then increases continuously with increase in pressure. Above this temperature, the value of Z increases continuously with increase in pressure. Thus, from the above observation, we may conclude that Boyle's law is obeyed only at very low pressure and moderately high temperature. Next one, deviation from Charles' law. According to Charles' law, the coefficient of expansion of volume of every gas should be same at all pressure. However, in practice, this is found to be so only at low pressure and considerable deviation sets in with the increase in pressure. Further, The gases which are more easily liquefied show larger deviation. Next one. Deviation from Avogadro's law. 1 mole of every gas should occupy a volume of 22.4 liter at NTP, which is not found to be true in any real gas. Again, as in the above two gas laws, the deviation are more in case of easily liquefiable gases. Example, ammonia and ethyl chloride at lower temperature and higher pressure. Next one is causes of deviation from ideal behavior. We have observed that the gas obey the ideal gas equation PV is equal to nRT only at low pressure or high temperature. However, if the pressure is high or the temperature is low, the real gases show deviation from the ideal behavior. The reason for the deviation is the following two assumptions made during the deviation of kinetic gas equation on the basis of which gas laws are derived. The volume occupied by the gas molecules is negligible as compared to the total volume of the gas. The force of attraction between gas molecules are negligible. However, the above two assumptions are true only at low pressure or high temperature, so that the distance between the molecules is large. In case the pressure is high or the temperature is low, these molecules come closer together and the above two assumptions do not hold. Hence, it is necessary to apply suitable corrections so the ideal gas equation so as to make it applicable to real gases. Next one. Necessary for Wonderwalls equation. As mentioned earlier, the ideal gas equation is not obeyed by the real gases at high pressure or low temperature. In case the pressure is high or the temperature is low, the gas molecules come close together and the above two assumptions do not hold. Hence, it is necessary to apply suitable correction to the ideal gas equation so as to make it applicable to real gases. Wonderwalls equation. As mentioned earlier, the ideal gas equation is not obeyed by the real gases at high pressure, at low temperature. In order to get an equation relating volume, pressure and temperature, which is obeyed by the real gases over wide range of pressure and temperature, a number of equations of state have been suggested, of which Wonderwalls equation is the total. Wonderwalls made correction terms in the ideal gas equation to account for the errors are introduced in result of the above two family assumptions. Volume correction. The assumption that actual volume of the molecules is negligible does not introduce any appreciable error at low pressure, but at high pressure, when the molecules are quite closer together, the volume occupied by the molecules themselves becomes a considerable fraction of the total volume of the gas. According to van der Waals, the actual free space available inside the vessel for the movement of the molecule is not the volume of the container. But it is actually the volume of the container minus the effective volume of the molecules. Correction. Volume is equal to V minus B. If instead of 1 mole we take n moles of the gas in the vessel of volume, V, the effective volume of these molecules will be NB. Hence here the correct volume is equal to V minus NB. Next one is the pressure correction. The assumption that molecules exert no appreciable intermolecular attraction is not justified, especially at high pressure, which the molecules are quite closer together. Consider a molecule A lying in the interior of the vessel. This is attracted by other gas molecules on all sides. Hence, the net force of attraction exerted on such a molecule by the other molecules is zero. However, a molecule B lying near the wall of the container is subject to net inward force of attraction or pull to the interior molecules. Further, the inward force of attraction will be appreciable at high pressure. When the molecules are quite closer together, the effect of such an inward pulse is dragging back of the molecules. Consequently, the measured and inward pull is dragging back. Pressure P with which the gas molecules strike the wall of the vessel is less than the pressure that would have been exerted in absence of such inward pull, that is under ideal conditions. You see in the slide clearly. This will tend to make PV less than RT and so will produce a negative. Under perfect deviation, say correction terms, P should be added to P to get the ideal pressure. Corrector pressure P plus P. The number of molecule pressure for unit volume in the interior bulk of the gas which one attracting the striking molecules. The number of molecules per unit volume striking the wall. Each of these terms depends upon the density D of the gas, hence correction factor P is directly proportional to A square. D is equal to 1 by V. P is directly proportional to 1 by V square. P is equal to A by V square. When A is proportionally constant, called the coefficient of attraction, its value depends upon the nature of the gas. Corrector pressure P plus A by V square. Substituting the value of corrector pressure and corrector volume in the ideal gas equation, PV is equal to RT. P plus A by V square, V minus B is equal to RT. This equation is known as Wonderwalls equation. The constant A and B are called Wonderwalls constants and their values depend upon the nature of the gas and independent of the temperature and pressure. D is directly proportional to N by V, D square is directly proportional to N square by V square, P is directly proportional to D square, P is directly proportional to N square by V square, then P is equal to A, Na square by V square. For N moles of the gas effective volume Nb, the van der Waals equation becomes P plus An square by V square V minus Nb, that is equal to nRT. Van der Waals equation is obeyed by real gases over wide range of temperature and pressure, hence it is called equation of state for the real gases. Units of van der Waals constant C and B depends on the units in which P and V are expressed. So P is equal to An square by V square. So today we discussed about van der Waals equation, derivation of van der Waals equation, and isotherms of nitrogen gases, and Wonderwall equation, deviation from gas laws that are the Boyle's law and Charles' law and Avogadro's law. These are the main important topics.